Welcome back. This is an Aleks homework video on calculating percent dissociation of a weak acid. Well, weak acids do not dissociate completely. So dissociation really is breaking the acid up. Even though that this is a covalent bond, it's breaking up into ions. You're going to have a hydrogen ion, and you're going to have its conjugate base of whatever else is there as a negative ion. And so if it's weak, it's not going to completely break apart into positives and negatives. And because of that, you're going to have some kind of equilibrium. That's kind of where we're going with this. It is an equilibrium problem. And so they're giving you almost nothing. They do have some stuff on the data tab on Aleks. So they've got your pKa, they've got your Ka for this acid, and you're going to need the Ka because the Ka is that's how you find this. You're going to do an equilibrium expression. So since I've got a balanced equation here that is reversible, meaning that I'm going to be making some acid and some conjugate base, or it's going to be in equilibrium between the original acid and the hydronium ion, then you're going to have an equilibrium situation here. So the Ka I just got from the data table in Aleks, and it happens for this acid to be 9.33 times 10 to the negative 6. And so I just made a K expression. The concentrations of your products divided by the concentration of your reactants. And remember, water is liquid, so we threw away everything that is not aqueous or gas. So we threw away water here since it's a pure substance. It's not counted here. So I simply have the hydronium times the conjugate base divided by this weak acid. And then I wrote down the K sub A. Okay, now since it's in equilibrium, I'm interested in the concentrations at equilibrium. So I have to do an ICE table to do this, like any equilibrium problem. So the ICE table here is really easy. It's a 1-to-1-to-1 correspondence. And as my acid breaks apart, I'm going to make a conjugate base plus some hydroniums. And so I've got a negative X and two positive X's. And so I end up with right? So this is, this is my I, this is my C, and this is my E. So at equilibrium, it's 0.49 minus X, and then X and X. Now, we're going to ignore this in a minute because this is so small. We've got a very, very small X, and so because of that, I'm just going to ignore it. I don't want to have, PhD level algebra in order to do a chemistry problem. So we're going to approximate this as a very, very small number, and so it essentially approaches 0. So we're gonna just use 0.49 in our math work in a second, which makes life a lot easier. So I simply just remember this is my expression, and I just put X in for my hydronium, I put X in for my conjugate base, and I put 0.49 in for my right here for my acid. And then when I just took the square root of that, I have X as 0.00213,815, whatever. Okay, so I've found the concentration of the hydronium or the conjugate base at equilibrium. So what we need is a dissociation. What is the percent dissociation? So to do the problem, as long as you know how to do it, it's very simple. You're going to have the concentration of whatever you made, whether that's the acid or the conjugate base at equilibrium, divided by, I think I wrote this twice, I'm sorry, divided by the base, or the initial acid, times 100%. Okay, so I simply took that, divided it out by 100%, got 0.436357%, and they asked for two significant digits. So for this one, it would be 0.44%. So as you practice, things that used to be so hard turn out to be much easier than you saw, as long as you've got lots of experience. So I'm sure you've had lots of experience doing this homework. I hope these videos are helping you.